So good morning, welcome. Um, let's see, I sent out a couple of announcements. Well, I sent out an announcement with a couple of subjects. So I've made a few changes to the syllabus, mostly just clarification of some things, but there was kind of a typo from where I had just copied this over from another semester where this was being taught, where it said that we were only meeting on Tuesdays. Which is not true. We're meeting every day except Saturday and Sunday. Let's see. For some reason, I can't see all of my own announcement. Weird. Oh, here we go. Yeah, so I clarified on the syllabus that I don't have an attendance. I'm not taking an attendance grade in the class. Let's see, what else? Yesterday's meeting, the recording of yesterday's, or not yesterday, day before yesterday's, has been uploaded to YouTube, and there's a link on the on the syllabus. I have uploaded the one from yesterday as well, but I'm not finished sort of chopping off the beginning and end where nothing's happening. So I'll put that on the syllabus as soon as that's done. Let's see. Web work is set up now. So the first web work, I believe, opens up tomorrow. I haven't taken a look at it yet, so I'll take a look at it after class today and just make sure that there's nothing that we haven't covered yet or haven't talked about. Let's see, what else? Oh, I've got a nice schedule on the syllabus now. It only has the first 4 days so far, but I'm gonna slowly fill it in as we move forward. It has the section from the class notes that we're going to be reading, the section from the Geary level book, and then there's also this William Trench book, which is a really good resource. So the reading assignment is going to be all three of these books. So it's 3 sections. Yeah, so the books are decent, but I've noticed there are a few kind of typos, but it's mostly grammatical things, so it doesn't really affect the content. Just sort of you have to correct what they meant to say in your head. Anything else?
I had a question about exams. Will those be open note or open text or anything?
That's a good question. So I haven't really. Sorry, my volume is suddenly really loud on. Cut it down a little bit.
I'm just in a loud place too.
Oh, that might be it.
Yeah.
So I haven't really come to a decision completely on what I'm going to do for that. My feeling is that probably what I'm going to do is allow sort of open notes. But for the problems, I'm going to expect that you write down all of the steps so that you very clearly indicate that you understand like what's going on. Because I have a feeling that there's going to be maybe some people, I don't know, maybe I'm a little pessimistic, but I think there'll probably be some people who, if I say no books and no notes, they'll just cheat and do it anyway.
That's how I've done it in the last few Zoom calculus classes too. So yeah, just show your work and send it in. And then there won't be any quizzes, right? It's just web work and then exams.
Yeah, I don't have any quizzes set up, so yeah, that's what it looks like it's going to be. It's just web work and the exam. But we'll have, well, I guess we'll have 4 exams. It is kind of difficult to do quizzes in a summer semester because we go through it so quickly. So between the web work and the quizzes, I feel like that's going to be a pretty dense assignment of stuff to do. Now, like I said in the past, I am recommending that you take a look at the exercises that are in the books, especially the Geary level book. some good exercises in there, and they have the answers included with them. So if you want to get some extra practice besides, the sort of thing that would be on quiz, a little extra practice or extra feedback, you can work some of those problems and then send your solutions to me for feedback, and I'll be more than happy to talk about those. Let me double check and make sure there's nothing else that I wanted to talk about before we talk about actual math stuff. Oh, there's a very good chance that I will be canceling class on Monday because I'll be doing my dissertation defense. And so I'll probably not want to have the stress of teaching on top of that. So there's a good chance, but I'll send out an announcement if that does happen. And one last look before we get started. Are there any other questions before we get started? The other thing I wanted to say is that because we're meeting live every day at the same time, and really the purpose of this is not to just sit here and listen to me lecture, but to ask questions about things that you don't understand. If this sort of turns into a situation, which is the feeling I get that a lot of sort of Zoom classes turn into, that it's just me sitting here talking and nobody's asking questions, and because everybody kind of feels like, it's weird to interrupt somebody in the middle of Zoom, or it's hard to figure out when it's okay to ask questions, things like that, then I get the sense that there's really no reason for me to actually be waking up in the morning and getting ready for a class like this, when I could just be recording lectures and sending them out on YouTube, saving myself a lot of effort. So I really like the purpose of me coming here in the morning when I'm not a morning person, very obviously, and doing this is I really want you to ask questions. So please do. So on that note, we'll get into the actual material for today. So let me start up my tablet here. Whiteboard. Okay. Oh, there's the leftovers from yesterday. Nope. Okay, so yesterday we had talked about like something on there. Yeah. Okay, so yesterday we had talked about a little bit about the slope fields, which was supposed to be the topic for today. And we used that to kind of segue into the existence and uniqueness theorem. Now, there's more that we could talk about on that. So I'm gonna try to work through a couple of examples, kind of make the sense of the existence and uniqueness theorem a little more precise. So remember that this existence and uniqueness theorem. So this is a theorem that only applies to first order ODEs. And so these are ordinary differential equations that have a special form. So the highest derivative that we have of, we're going to call y is going to be our solution. So this is what we're looking for. A function that we're going to call y in terms of a single variable or dependent upon a single variable, and we'll call that variable x. And this has the form y prime is equal to something completely in terms of x and y. So we can rearrange our ODE so that we put it in this form. And this is what this kind of way of stating this was what allowed us to look at the slope field of this thing. But what this theorem said was that if f is continuous, and f sub y, or in other words, the partial of f x y, is continuous. So if these two cases hold in some region around an initial point we'll call x0, y0. So this is a function of two variables. So we have to talk about possibly a region around the point in two-dimensional space. If these two conditions hold, then a solution y of x exists and is unique. And I'm just going to put this in a intuitive sort of just English language way of writing this. Near x0, y0. And we called this a local solution, or a local condition on a solution. Right. So we have that this solution exists, and not only does it exist, it's unique. But we can only say this for sure around some region around x0, y0. Now, if we have some part of this, so the notes go into a little more detail than the Geary level book. If we just have this condition, that f is continuous, which is all that we were talking about when we were looking at the slope field. We were just looking at them being continuous. We didn't, say anything about the fact that the partial derivative with respect to y was continuous. Well, this guarantees existence. However, it doesn't guarantee uniqueness. Okay, so that's a little twist in it that sorry, I'm trying to make room on my desk. That the notes talk about that the Geary level book doesn't. So I want to do a couple examples of how this works out in practice, because we really only looked at one example yesterday. But that looks at this distinction between when it could possibly exist and not be unique, and also when these solutions are just local. So first of all, when we looked at this differential equation, so y prime is equal to ky, and we had an initial condition, we just called it y of x0 equals y0. So really any initial condition. Actually, let's just go ahead and say this happens to 0, and we'll call it capital C. I think that's what we called it last time. So what we get as a solution for this is y of x is equal to c e to the kx, right? This was the so-called population growth example, population growth or exponential growth. In this case, this is defined. Let's just say it's defined. Yeah, I'll say and is unique globally. So in other words, for any for any x on the real line, right? We know that the exponential function is defined for any input x. There's no places where it's undefined. And we have a unique solution because we know what the c is, and we know what this, well, supposedly we already know what the k is, but we're given the c as part of the initial condition, right? So this is kind of a nice situation. These are the situations that we want. We want a solution that gives us an answer to our problem for any input, not just for a particular input. Okay, so let me switch over to the first example that I want to look at. We did look at this briefly yesterday. This was, here we go. So here we have our differential equation is y prime equals y squared, and y of 0 equals a. So that'll be our initial condition. So without going through the work of getting the solution to this again, our solution, simply stated, it's y of x is equal to 1 over a minus x. And to simplify this solution, I'm going to rewrite our initial condition as 1 over c, so that I can kind of have some uniformity and just call this, just write this as 1 over c minus. Okay. Now, this is undefined at x equals c, right? Because what we end up with is we end up with a 0. And if we draw this, we would have something sort of like this, where here x is equal to c, and then we have, so it kind of blows up when x is equal to c. It goes to infinity or negative. So in this case, we don't have a global solution. So we say that this is our initial point. So this is 0, 1 over c. That's our initial condition. That's the point that we know that our solution goes through. And so when we talk about the solution to this, we're really only going to talk about this piece of it right here, right? So this chunk of the function is going to be considered our solution to the initial value problem. Oh, by the way, I'm saying initial value problem out loud. Probably faster to just say IVF. If you see IVF in the books, this is what they mean. They mean, I'm gonna write it up there. Initial value problem, IVF. Maybe IVF stands for something. Okay, so we're really going to talk about this solution as just existing on the interval from negative infinity to c. Okay. So we have a solution, but it's not a global solution. It's just a solution on a certain region. So that's the first important distinction. This theorem doesn't give us global results always. Sometimes we get solutions, and oftentimes that's what we want, is a solution where it's defined everywhere. It's defined for all values, all input values x, but this is not always. This is also a good illustration that just looking at this differential equation, we, for example, y squared, this is a simple function. This is a function that we've been dealing with for, ages and ages. It's really nicely behaved, and we might not expect that, a differential equation that contains such a simple function ends up having this discontinuity, this kind of not so nice property of the solution. So just an illustration that oftentimes differential equations behave in a very unexpected way. Okay, now the next example that I want to look at is actually in the class notes. So these are the notes that are written up by Dr. Oceanine, and they go into pretty good detail. And there are occasionally typos. They're not too disastrous. Let me see if I can find this. Oh, actually, let's take a look in. So if you're able to go ahead and open up the Jerry Level book, and we'll take a look at this is in section. It's in the slope fields section. Fields section. And this is exercise 1.2.8. I don't believe they have the solution to this one in the book, but they call this one challenging. So maybe this will be a good exercise of what we've been looking at. So the differential equation that we're going to be looking at in this case is going to be y minus x times y prime is equal to 0. Okay, this is a differential equation. Well, let me come back to sort of the properties of this one in a second, but I'll just state this for now. And the first part of this question says, find two distinct solutions. So these are functions of x. Y is a function of x that pass through, or when you plug in 0 into the function, so it passes through the point 0, 0, or when you plug in 0 for the x value, you get 0 out as the y value. So I'm just going to give you a minute to think about this. Do this just based entirely upon guessing. So, if you look at this, you might think there's some obvious guesses that you might try, and just try those out and see if they fit the differential equation. So I'll give you just a couple of minutes. So has anyone come up with one solution to this?
I wrote down y equals x.
Y equals x?
Yeah.
Yeah, let's give that a shot and see if this works. So y equals x. We plug this in, we get x minus x times, well, I guess it really doesn't matter what the derivative of y is right here, but in any case, we get that that's times 1. And this is in fact equal to 0. Okay. And we should check the initial condition. If we plug in a 0 here, we get 0. So yes, that is one possible solution. I'm wondering if anyone can find.
What about y equals 0?
Y equals 0 is actually the other one that I was thinking of. I don't know if there are any other solutions to this. But yes, that definitely works. Let's see. We get 0 minus x here, And then the derivative of 0 is just 0, so we can 0. And I think that's probably it, but I'm not totally sure. I guess we have to assume that either this is 0 or this is 0 just because of the factorization. And yeah, there's only one possibility for the left factor and one possibility for the, oh no, for the right factor, we get any y is equal to c. But of course, the initial condition determines what c has to be, right? Any constant. So this initial condition forces us to be equal to 0. Right. So these are two distinct solutions, and they both go through the initial point. And so it really seems like this violates our existence. I'm going to abbreviate this: existence uniqueness theorem. Question mark. Does this violate our existence uniqueness? Okay, so does this actually disprove our uniqueness theorem? Have we proven one of the great mathematicians of history wrong with this example? That would be nice. That would be a nice. I think we all get A's for doing something on that level. Unfortunately, no. Does anybody know why?
Well, for one, there is a solution to it, and since the solution exists, it is unique.
In this case, the solution is not unique, right? We actually have two. We have two solutions. So as Tyler was pointing out, both of these satisfy this initial value problem. So on the surface, it does look like we've found a counterexample to this theorem. I'll just go back to our theorem here and take a look at it. So it does tell us that, I really hate working. There we go. It does tell us that it exists and that it's unique. I'm going to just give you a second to think about it. We have y minus x, y, oh, sorry, y prime equals 0. So if we rewrite this in this form right here, and this is kind of a little bit of a rough example, because what we end up with is y prime is equal to, I think I need to wear gloves or something so that when I touch the screen, it doesn't start doing. We get y prime is equal to 0 over y minus x. And our sort of algebraic instincts tell us that this thing is just equal to 0. Unfortunately, that's not always true. That's not true when y is equal to x, right? When y is equal to x, this expression is undefined. So what are we trying to show? We're trying to show that f is continuous and that the partial of f with respect to y is also continuous in some region around x0, y0. And where is that? Our x0, y0 is precisely at a point where x equals y. So what we get is that this f of xy right here, this thing is not continuous in some region around 0, 0, or initial. And so that's the reason that we don't have a contradiction here. Okay, so that's an interesting example. Let me see if I have time for this. I'm going to look up the example that's in the notes as well. Okay, so let me clear the screen. Hopefully you have this. Does everybody have this sort of committed to paper or memory, the statement of the existence and uniqueness theorem? Okay, I'm going to clear the screen. I can't scroll back. Okay, so here's an initial value problem. Y prime is equal to 5/3 y to the 2/5. Y of 0 is equal. Okay, now we know how to solve an initial value problem like this. Go back and make sure I'm not missing anything. Okay, so I won't go through the steps of working this out, but we'll I'll just give you the solution. So the solution to this is y of x is equal to x minus some constant c to the 5/3. And we can see that this is a solution because if we take the derivative, we get 5/3 x minus c to 2/3, which is if we plug this back in, or we plug y into that, we get that. Sorry, if we replace the power of this thing with y, so we take this and put it into here, what we end up with is this is equal to 5/3 y to the 2/5, which is what we're looking for. And when we plug in oh, this is our general solution. Sorry. We also have that y of. Sorry, give me just a second. I thought I had a good example prepared here, but maybe this is going to take us a little bit. So I'll just tell you that this is. You want to take a look at this example. It's an interesting one, but it takes a little work to go through. We're already over halfway through class for today, so maybe I'll move on to slope fields. So this is in the notes. This is example 2.3, page 6. I'm just going to skip over that for today. Okay. Now let's take some time to look at slope fields. That's actually what we're supposed to be talking about today. So for that, I need to reconnect my keyboard in order. Get out of screen share here. So I found a nice Desmos workbook. Okay, here we go. So I found a nice Desmos workbook for looking at slope fields, and so I've put this into the into our schedule page here. And we'll just take a look at this. Okay, so I'm gonna kind of rearrange things so that I can Wait, what's going on here? So am I sharing my whole screen or am I just sharing the window? Can you see the whole window? Like when I do this, it's not like blocking out part of the window so you can't see it. Okay, good. You know, thank goodness this is the last time that I'm ever going to teach something on Zoom. We'll get through this. We'll get through the next 7 weeks and then I'll be done forever. Okay, so okay, 2 of them open. Let's leave that one. Okay, so this is really nice. It lets you take the if we say that our derivative of y with respect to x is equal to this function of x and y, then we can put that function in here. And so they've given an example of 2x over y, and that will plot a slope field for us. And then we also have this movable point here, so we can kind of go around and see how this the slope that's defined by this changes continuously. Now I'm going to change this to the population growth example. So I'll take the constant to just be 1, and this is what we get for our slope field for population growth or exponential growth if that constant, the k, is equal to 1. So if I just kind of move around, you can see how this slope changes as we move. And let's go ahead and try to plot the actual solution. So we know what the solution to this is. It is e to the x. Right. So if that's if our initial condition is 1. So if our initial, I need to move this. I'm not going to be able to see you at the same time I'm talking about this side. If you have a reaction, you'll have to say it out loud. Okay, so you'll see that this this slope field matches perfectly with the tangent line along this. And so just like we were talking about yesterday, you can think about you have an initial condition for this differential equation, then you can just sort of plop your initial condition down here somewhere, and then just follow the slope field, and that slope field will tell you how the rest of the solution proceeds. Now, if our initial condition was that we started off with a population of 3, and that would be 3 right here, and you see that again, we have a solution that I just think these look really nice. This is a nice graph, right? You can see how the slope field tells us exactly how the solution is going to proceed as we move forward in the x direction. So let's take a look at another one. So it's saying let's sketch the slope field for this this example that we were looking at, y prime is equal to y squared. What is this like? It's kind of similar to the other one, except that it goes up faster in the positive direction. But it's also pointing upward down here on the negative side. So if I zoom in, it does not automatically get fine. Okay. So what did we say the solution for this was? This was supposed to be 1 over 1 minus x. And indeed, it does look like as we go here. So this is where we have our discontinuity in the solution. And what you see is that the as we get over here, the this thing blows up towards infinity. The slope field keeps getting higher and higher. Okay, what about a different initial condition? So we said that y of 0 equal to 1 over c. And so if we want our initial value at x equals 0 to be 3, this should be 1/3. And indeed, that's what you can see the slope. So let's try one of the different. Okay. So is it possible to solve the equation y prime equals y times square root of the absolute value of x for y is equal to 0? Well, let's just plug this into the slope field and see what we get. What was that? Y times square root. Okay. So this is, let's get rid of this no longer, the proposed solution. So this is the kind of slope field we get, and they give us a, get rid of one of yeah, y of 0 is equal to 0. So in this case, we have at 0, 0 here, what do we have? Is this function continuous? It's definitely, I guess it's not continuous. There's a discontinuity when we go from positive x to negative x. Is that true? No, that's not true because we're looking at the absolute value of x. Okay, so we do have a continuous function. This thing, however, is well, it looks like we should have that. Okay, so maybe let's skip this example. So this one, what happens to the slope field around here? So it looks like in this region, it nothing unusual happens. Skip to a different example. Okay, so this example where we had two distinct solutions. So what does the slope field look like? Oh, we can't. Sorry, I apologize. The course, I know it seems really scattered right now. It's because I'm working on like 100 things at the same time. This will all settle down by next week, I promise. And we won't have these kind of problems where I'm trying to come up with examples to talk about. Okay. So maybe let's take a look at this one. Sketch the slope field for y prime is equal to y cubed. Can you visually find the solution that satisfies y of 0 is equal to 0? Okay, so this is our sketch. It looks like as we go through, oh, first of all, let's talk about this this function. So this is definitely continuous, and the partial with respect to y is also definitely continuous, right? Because this is just a polynomial y, and so we expect there to be a solution and a unique solution. And if we look at this, what does this look like? It looks like very near here, we get a slope of 0, right? And so what we should have is that just visually from this, the solution that passes through the initial point 0, 0 should just be the function y. Okay. And let's take a look at this one. Actually, I'm gonna give you another. This is a problem that I want. So let's look at exercise 1.2.6. So take a second to look at this and try to match these with the three possibilities. So we have y prime is equal to 1 minus x, y prime is equal to x minus 2y, and y prime is equal to x times 1 minus So just take a minute to look at that and let me know when you have an idea for how to match up.
I know that the y prime equals 1 minus x matches with b just because I looked at when x is 1, the slope should be 0. So that was what I did first.
Yeah, that makes sense. So we've got, it looks like maybe it's slightly different from 0 here, but we are expecting, yeah, when x is equal to 0, we should just have a flat slope. And then as x increases, it should become negative, and as x goes in the negative direction, it should become more positive. So that's a good justification for why this one has to be. Also, like you said, we're looking at x equals 1 has to be 0, and none of these two have it. So by process of elimination, it must be b. Yeah, that's a good answer. So there's another thing to notice about this, and that is that this y prime depends only on x, whereas these other two depend on y. So there's some dependence on y. So as y changes, we should see a change for the other two. Whereas for this one, we should only see a change in the x direction. And we do in fact see that. So in the y direction, we see no change. In the x direction, we do. Okay, so we've eliminated one possibility. What about the others?
For y prime equals x times 1 minus y, I think it needs to be a, because if you look in the middle when x is 0, all of the slopes are 0, and that's what y prime would be whenever you solve with x for any
Yeah,
number.
right. That's a good answer for that one. Again, we see something. There's a very easy to spot distinguishing pattern here, right? The x is equal to 0, we should have 0 for all of these. Similarly, if we have y is equal to 1, then we should have zeros here too. And so we see, it looks like when they plotted these, they were slightly off from exactly 1, but it's pretty close. And then by process of elimination, we have the last one. So maybe let's take a look at this and see why we might find a distinguishing feature of this one that would tell us that it has to be C. So if we look at this, we'll do a similar thing. We'll say when is the slope exactly equal to 0? And that's when we have x is equal to 2y. In other words, on the line y is equal to 1/2 x, which is that line that goes through the origin has a slope of 1/2, then we should see slopes that are at least really close to being 0. And that's exactly what we see here. Okay, so that's a nice example for slope fields. So take a look at this one. This is another example where I haven't looked at the web work yet, but I'm like 99% sure that they're going to have a problem that's just like this. It's like a classic web work style problem.
Would y prime of sine x go with c? Because if you take sine of 0, then you're going to get a slope of 0. But if you take sine of 1, you get a slope of 1. So it either goes in the positive or negative direction.
Yeah, so I agree with you there. If we have x is equal to 0, we should have 0. And yeah, we see this kind of pattern. As x increases, then the slope kind of increases and then decreases and increases in the same kind of pattern that we would have for sine. So yeah, that's a good idea for this one. Now another possibility for this one is that if we look over here, again, we have the same kind of situation with the first example from last time, which was that this function depends only on x, whereas for the other two examples, we have some dependence on y, and here we have some dependence on y. So as y changes, we expect to see some change for these two, whereas for this one, as we go in the y direction, it should be totally constant. And so that's it's kind of just building on the reasoning that you were talking about, which is that if we look in the y direction, first of all, here in the y direction, we see exactly the same thing everywhere. And then on all of these other vertical strips, again, we see the exact same slope. Yeah, that's very good. We should have y prime is equal to sine c. So we've narrowed it down to 2. Here for the one.
So for y prime equals cosine y, same thing with letter C. We shouldn't see any variation with x, so that would be A.
Yeah, exactly. This is completely in terms of y, so there's no x involved. We call this kind of thing where it's not, where our function is not dependent on x, we call this, or the independent variable, we call that autonomous. And so if we think of this as, instead of going in this is in the x direction and y direction, which we normally think of spatial dimensions. If we thought of this as the horizontal direction being time and the vertical direction being the output of the function at a particular time, then the solution of this doesn't change with time. What we have is like a steady state solution. So as we go forward in time, the solution doesn't change. Okay. And so we've narrowed it down to only one possibility, and that is, I guess, the more difficult one. We can't use the technique that we've been using so far. This one is in terms of both y and x. Now, is there anything that we can do with this one in order to figure out what it should be?
Well, I thought you were asking, my bad.
No, go ahead.
At y equals 0, the slope should all be 0 because y is on the outside.
Yeah, exactly. We have this whole thing multiplied by y, and when y is equal to 0, that makes the whole thing equal to 0. A little bit more difficultly, if we could figure out where cosine of, what do we have? Cosine of pi over 2. So if we could figure out where pi over 2 is, then we should have zeros as well. And so it looks like we come pretty close to it, maybe right in between. Right. So when x is equal to pi over 2, we should also have a 0 slope. But we should go with the easier one, which is y is equal to 0. Why do hard work when you and accomplish the same thing? Depends on what we're trying to do. Okay, are there any others that we want to look at? So there's some interesting examples here. This one is just a problem where we're sketching the slope field, so we can definitely do this with the Desmos tool. So let's see what this looks like. Exponent. So it's e to the x minus y. There we go. Okay. So the question asks us, can you guess a particular solution by looking at the slope field? So trying to click on the tab. There we go. Okay. So do you have any guesses for a particular solution on this one? it does, we don't get an initial condition. So we can have our solution pass through anywhere in this slope field. So maybe we pick a particularly easy.
Y equals X.
Yeah, that looks like a perfect solution. So if we're able to sketch this thing or have a computer draw it for us, then that would be a solution that's suggested to us immediately. So this, all right. Nope, wrong direction. There we go. The slope field immediately suggests to us that possibility because we have a straight line going through here, and so anything that's right on this line will continue to go in that direction. What we also see is that if we have any initial condition besides that, so if we start like maybe right here, so let's look at, we'll kind of try to follow the slope field, and it kind of goes towards this line and creeps in towards it, and it gets closer and closer to this line y is equal to x. So what we see is that not only do we have y is equal to x solution, and well, we can go back and look at the differential equation and see if y is equal to x, we have e to the 0 is, we have just e to the 0 here for their derivative, and so our derivative is just 1, right? And if y is x, then the derivative of x is just 1. So this is also a solution that we possibly could have got just by guessing. But we also have that, let's see. I'm going to cheat for a moment and use Wolfram Alpha and say, what is the general solution here? I'm not expecting it to be anything really simple. That's not too bad. It's log of some constant plus e to the x. So let's try that. Okay. So it's natural log of, let's say our constant is 1 plus e to the x. Of course, if the constant that we've put here is 0, that would correspond to our initial condition where we're already on this line. And so that just gives us x, right? So that's solution. And what do we see? We see that something, as we go sort of backwards in time, we're going to something that approaches 0. But as we go forward in time, we approach this this solution that we had, the particular solution that we had before, which is we start approaching x is equal to y. And we can see that from our solution here. As x gets really large, this 1 plus e to the x becomes a very small contribution. Basically, as x gets really large, this 1 plus e to the x becomes practically nothing. We could basically just ignore it. And so we see from that as we go towards x is equal to, as we take the limit as x goes towards infinity, then what we get is that the solution starts to behave just like that particular solution that we saw before. Okay, I have successfully filled up an entire hour. I promise this is the last class where I won't have things prepared. So I've got most of my stuff kind of squared away. So, like I said in the announcement, office hours are now going to be like immediately after class. So I'll just stick around if you have any questions. Otherwise, I'll see you tomorrow, and have a good day.
Bye. Thank you.
Yep, no problem.